All right, so now let me remind you that what we did from last time. So we have the double angle identities for sine, cosine, and tangent. And unfortunately for cosine 2 theta, right, there are two more variation. I'll put it over here. Cosine 2 theta could be also written as 2 cosine square theta minus 1, or if you like sine square, you can have 1 minus 2 times sine square theta. Okay. I believe that when you get to Calc 1, you will see most likely that you're better off with lower powers of those trig functions. Just like, in algebra, whenever you see like x squared, x cubed, or x plus 1 entirely to the third power, right, that's hard to deal with. And things is worse with the trig functions. That means that instead of looking at double angle identities, as you normally go from the left-hand side to the right-hand side, we're hoping that we're sometimes going from the right-hand side of those two identities, where it has the square of the cosine, square of the sine, to the left side, so that we are reducing the power by getting bigger angles. Okay, so once again, it's easier to deal with lower powers. That's why if you see higher powers, you want to reduce the power, and that's why we're introducing the what we call power reducing formulas. Now for those ones, they are now if you actually take a close look at the first two, they are strictly from the two additional versions of cosine 2 theta. Oh, somehow there's a typo in the author's PowerPoint. All right, so the first one is 1 minus cosine 2 theta instead of 2 cosine theta. The 2 should be inside the function. Well, cosine 2 theta is cosine of the double angle. Well, 2 times cosine theta is twice of the function. Right? Yeah. So now, as you can see, that it's called power reducing. You use them when you see square or higher power of those trig functions. You want to trade a bigger angle for a lower power, right? Like I said, you're better off with lower powers. But it's interesting to notice that if you had the second power in the first place, once you reduce the power, the angle gets doubled, right? And it's always the cosine for some reason. And later on, you don't have to remember for the triple power, or the triple angle. But if you ever realize you have to reduce the power up to the fourth, to the third, to the fourth, to the fifth, and the angle will be getting bigger by the same amount of times as the power. But at least that the good news is we only need to know the power reducing for the second power of those trig functions. Okay. So now today I'm only going to show you one example because I just want to be consistent with all my classes when it comes to pacing. But that example, well, of course, you know that for these kind of identities stuff, it will be some algebra, right, and a verification of identities and some kind of tips. But I can assure you that the example you're going to see on the next slide won't be on the test. Right? It will not be on the test because that's not what we like to evaluate you guys in a test. But the reason why I still want to show you is it's a good demonstration of these identities, right? Since you just learn it, right? It's like, when you learn some new tools, go ahead and play with it for no reason, right? But you're not going to seriously use those tools in the way you see, in the next slide. Anyway, so that's the problem in the book, only based on my own understanding. It's only for illustration purposes. So they say that you have sine to the fourth power, but they want you to write that expression in terms of some trig functions with powers no greater than 1. So they want to reduce the power. But the tools we have can only help us with second power, right? I'm going to write it down so you guys can take a look. Now, even though that we're using theta, but I hope you know that x and theta are the same. It's just different labels. So to reduce the power of the sine, you get 1 minus cosine 2 theta over 2. Okay, so again, reducing the power, the price you get is doubling the angle. All right, cosine squared theta can be written as 1 plus cosine 2 theta over 2. All right, so those are the tools we have. Now, sine to the fourth cannot be reduced, into some lower power right away. But if you write it as sine square, and then to the second power, at least that you can do something about the sine square. Okay, because squaring sine square is going to get you the sine to the fourth. So then what is sine square? Reduce the power, you get a 2 on the denominator, right? 1 minus cosine 2x, right? Since I'm dealing with x, I'm going to square the whole thing. Now, squaring the fraction is equivalent to just square the numerator, right? So you get 1 minus cosine 2x square over square root of 2, which is 4. And I hope that you realize you need to FOIL or expand the numerator. We're going to get the perfect square trinomial, right? So try to take the formula here, right? We have the sum or difference of two terms. So you're going to get square of the first term, right? Square of the second term. We have a middle term here, which goes like twice as much of the product of the first and the second term with the plus. If it was a plus, right? It's a minus, there you get a minus. So in this case, we have the capital A, right? Here, but that's just going to be a 1, right? And the B is just cosine 2x, right, with a subtraction. So the pattern is going to work out as the first term, 1, gets squared, right? There's a minus sign. 2 times first term, which is 1. Second term will be cosine 2x. You have the second term, right, which is the b, right, gets squared, but the cosine 2x will be cosine square 2x. Okay, over 4. Well, then we realize they want the expression of the trig functions with powers no higher than 1. So we're fine with the constants, right, and the cosine 2 theta, but we have to deal with the cosine square 2 theta. Right, so we can reduce the power once again. I'm going to copy the 1, 2, cosine 2 theta, 2x. Now for the square of the cosine. So notice that if you reduce the power, you double the angle, right? So if the angle has been already doubled, right, it's 2x. When you double it again, it becomes 4x. Right, so that means it becomes 0. There's a 2 on the bottom, right? And it's 1. Now it's plus cosine of 4x. Because you notice the angle will get doubled every time you reduce the power. See that? If it was theta, right, cosine of square root of theta becomes 1 plus cosine 2 theta. And therefore, if it was cosine squared 2x, then when you reduce the power, you're going to have to double the angle. doubling 2x is going to be 4x. So everything's over 4. And technically speaking, if you leave it like that, you're not wrong, because if I'm not seriously checking if you can write that expression in terms of, those kind of a compact conventional form, then I mean, I'll give you full credits, if you do have a question like that in a test, but not very likely, right? So like I said, that's not going to be something we'll check. But you know that if you could simplify by writing the expression with less denominators, right? Or if you see some like terms you can combine them, do that. Okay. And in this case, all you have to do is split the fractions, split the numerator. We're going to have to do it for 2 rounds. The first one's going to be for the fraction on the numerator, right? Then you're going to do it again for the entire fraction. So I'll do the first one here by splitting those 2 guys. I'll write it as 1/2, right? Which is 1/2. And the second term is going to be cosine 4x over 2. We know that there's a 1 in front of the cosine 4x. It'll be 1/2 cosine 4x. This is just like, the distributive property of division, right? So everything's over 4. But I hope that you can combine maybe 1 and 1/2, right? The odds would be 3/2. They have -2x, -2 cosine 2x, but 1/2 cosine 4x. They don't combine, so just copy them. That's 1/2. So now you have 3 terms in the numerator, all over 4. You slip it one more time, right? The first guy is going to be 3/2 over 4. You do the keep change flip, you get 3/8. Second term will be -2 over 4, right? As the coefficient, that will be -1/2. And the last term will be 1/2 over 4, right? So you're going to get 1/8. Okay, and that turns out to be the power reduced form of cosine sine to the 4th power. Okay, so that could have been an identity, right? For the higher power of sine, but like I said, this is not something that you need for our test, right? Not even this problem. Like I said, it's only for illustration of those 2 power reducing formula for sine squared and cosine squared.